On this question, we want to follow a 9-step graphing strategy to sketch the graph of the rational function. Our rational function, f of x, equals x squared plus 4x minus 45 over x plus 5. Our first step will be to find the domain of this function. And for rational functions, division by zero, actually for any functions, division by zero is undefined. But especially since we have rational functions, we have variables in the denominator, and the possibility of dividing by zero can occur. So we want to set the denominator equal to 0 to figure out any restrictions we might have on x. So we'll set the denominator equal to 0 and solve. That gives me x equals -5. This is our restriction, because if we substitute a -5 in for x, we would have -5 plus 5, which is 0, and we'd be dividing by 0. So we have to exclude -5 from the domain. On the number line, we would mark -5 as excluded, but include all the other numbers on the number line. And we could write the domain as -infinity to -5, union with -5 to infinity. That's the domain of our function. Okay, on the next part, we want to find out if there are any removable discontinuities. This is another name for having a hole in the graph. So to find out if we have any removable discontinuities or holes in the graph, we need to see if there are any common factors between the numerator and denominator. So for our function, f of x equals x squared plus 4x minus 45 over x plus 5, we're going to factor the numerator. And the numerator factors to be x and x. Multiples of 45, we'll use 9 and 5. I guess that's factors of 45, not multiples. And I'll do a positive 9 and a -5. And so as we look at this, there are no common factors between the numerator and denominator, and so there are no holes. So since there's no common factor, we know that there are no holes in the graph or removable discontinuity, no removable discontinuity. And the next thing that we're going to check for is symmetry. So what we're looking for is to see if this graph has origin symmetry or y-axis symmetry. So if we have origin symmetry, then that means that our function is an odd function, and it would follow the property that f of -x is equal to -f of x. If the function has y-axis symmetry, this is called an even function, and it would follow the property of f of -x equaling f of x. So this is the test that we're going to do to determine if our function has symmetry. We're going to calculate f of -x and then compare it to f of x to see if it is the opposite of the original function or the original function. So let's write out our function here. Our function is f of x equals x squared plus 4x minus 45 over x plus 5. And I'm going to calculate f of negative x. That's negative x squared plus 4 times negative x minus 45 over negative x plus 5. I'll do a little bit of simplification. Negative x squared simplifies to be x squared. Positive 4 times negative x becomes negative 4x. Minus 45 carries down. Minus x plus 5 carries down. And what I want to do is compare this to the original function. And they do not look equal to each other. You have an opposite sign here and an opposite sign here. So they're not equal to each other, but what I want to see is, are they opposite of each other? So let's think about that. That would be negative f of x. Negative f of x would be multiplying a negative times the function x squared plus 4x minus 45 over x plus 5. And in that case, you would have to distribute that negative to all the terms in the numerator. If that happens, you would have negative x squared minus 4x plus 45. And that's not the same as this right here. And so it doesn't fit into either category of being even or odd. So we're going to say that this function has no symmetry. The next thing we want to do is find the y-intercept. To find a y-intercept, we're going to let x equal 0. So f of 0 is equal to 0 squared plus 4 times 0 minus 45 over 0 plus 5. In the numerator, that simplifies to be negative 45, and in the denominator, that simplifies to be 5. Negative 45 divided by 5 is negative 9, and so the y-intercept for this graph is 0, negative 9. For our next part, we want to find any x-intercepts. To find an x-intercept, we're going to let y equal 0, and for our function, that's f of x. F of x is the same thing as y, so we're going to let f of x equal 0. So we have 0 equals x squared plus 4x minus 45 over x plus 5. We'll solve this equation by multiplying both sides by the denominator. On the left-hand side, 0 times x plus 5 is 0. And on the right-hand side, we've multiplied by the denominator, so it cancels with the denominator. So we're left with the numerator, which is x squared plus 4x minus 45. We can solve this quadratic equation by factoring, and it factors to be x and x, 9 and 5, with a plus on the 9 and a minus on the 5. I would set each factor equal to 0. X plus 9 equals 0. X minus 5 equals 0 gives me x equals negative 9 and x equals positive 5. So we have two x-intercepts, one at negative 9, 0, and the other at 5, 0. For our next part, we want to look for any vertical asymptotes. Now earlier, we noticed that there were no common factors, which is an important first step for looking for vertical asymptotes. You want to make sure that your function is reduced, your fraction is reduced to having no common factors before you look for vertical asymptotes. Once you've established that you have no common factors, then you'll set your denominator equal to 0 and solve. And that gives you any values of your vertical asymptotes. So for this function, we have a vertical asymptote at x equals -5. Now we're going to look for horizontal asymptotes. Our function is f of x equals x squared plus 4x minus 45 over x plus 5. And we need to look at the degree of the numerator. The degree of the numerator is the highest power from the numerator, and that is 2. And the degree of the denominator is the highest power on x from the denominator. That would be m being 1. And anytime the degree of the numerator is 1 larger than the degree of the denominator, you're going to have no horizontal asymptotes. However, you do have something called an oblique or a slant asymptote. And you can find that slant asymptote using long division. So you would do it this way. You would take your denominator and divide it into the numerator using long division. And what you want to do is match the first term from here with the first term from here. So you would multiply x times x to get x squared. And x times x would be x squared. X times 5 would be 5x. And then you're going to subtract, and you subtract by changing the signs. That gives you -x. And you carry down the next value. Then you repeat that process over again. Now you're trying to match this x with this -x here. So you would need to multiply by -1 to do that. -1 times x is -x. -1 times 5 is -5. Then you want to change the signs to subtract. And you'd be left with -45 plus 5 is a -40. Now we'll stop with the division, and you're able to say what your slant or oblique asymptote is, and that's this right here. So we have a slant asymptote, which is at y equals x minus 1. So I'm almost ready to start graphing our rational function. So I've written here a summary of everything that we figured out so far. We have a vertical asymptote at x equals 5. We ended up with no horizontal asymptote. We have a slant asymptote at y equals x minus 1. We have 2 x-intercepts, one at -9 and one at +5, and a y-intercept at 0, -9. So I'm going to put this information on the graph, starting with my asymptotes. I'm going to use my ruler to help me. So I'm going to draw my vertical asymptote at x equals -5. And we're going to draw that with a dashed vertical line. And then we have a slant asymptote, and our slant asymptote has a y-intercept at -1 and a slope of 1, so I'll rise 1 and run 1, and I'll connect those 2 points with a dashed line to indicate where the slant asymptote is. And then I'm going to mark where my x-intercept is. I have an x-intercept at -9, 0. I have another x-intercept at 5, 0. And I have a y-intercept at 0, -9. So what I want to do now is to figure out how to draw the curve in these different sections of the graph. I have a few points. I have the x-intercepts and y-intercepts, but until I have points in every section, will I feel confident on how to draw the picture. So I'm going to make a chart, choosing a few extra values of x so that I can graph my, draw my lines in every single one of the sections. So for my x's, I've got -10, -6, and +6. What you want to do is you want to make sure that you pick a few values that are in each section separated by this asymptote here. So we've picked something to the left and a couple points to the right. I'm sorry, we've picked a couple points to the left of that asymptote and a point to the right. And we're going to substitute that into our function to figure out our y values. So I'm substituting that in for my f. That's -10 squared plus 4 times -10 minus 45 over -10 plus 5. -10 squared is 100. 4 times -10 is -40, and minus 45. In the denominator, -10 plus 5 will be -5. 40 minus 100 minus 40 will be 60, minus 45 will give me 15. 15 over -5 is -3. So that gives us an extra ordered pair to plot. Let's do the same thing with the next one. That's a -6 squared plus 4 times -6 minus 45 over -6 plus 5. -6 squared is 36 minus 24 minus 45 over -1. So we have 36 minus 24 is 12. 12 minus 45 is -33. And -33 over 1 is a +33. Okay, let's do one more. 6 squared plus 4 times 6 minus 45 over 6 plus 5. Got 11 in the denominator. 36 plus 24 minus 45. 36 minus 24. Sorry, should be doing plus 24. Minus 45 gives me 15 over 11. And 15 over 11 is approximately 1.36. So our ordered pairs that we just got are -10, -3, -6, and 33, and 6 and 1.36. I'm going to plot those additional points on my graph. -10, -3 would be about here. -6 and 33 is way off my screen up here. And 6 and 1.36 would be about right here. So we have a few points now, and we're going to use the asymptotes as guides on how to draw the graph. Remember, the asymptotes are kind of like fences blocking the line in. So these 3 points on the left here, they're going to connect to each other. But then this vertical asymptote, sorry, my pen's not working. This vertical asymptote and the slant asymptote are kind of fencing in that point of the curve. So the graph will get closer to this vertical asymptote and closer to the slant asymptote. And then over here, these 3 points will connect to each other, but it will be fenced in by this slant asymptote and this vertical asymptote here. So it's going to start following the slant here and start following the vertical asymptote here. And so we have our graph. Thank you for checking out my videos. Have a great day.